All right, welcome to Earth Science. We're going to start with divergent boundaries. All right, what I'm going to do here, I'll do the note sheets like as per usual. I've got multiple steps here. 1, 2, 3, 4. You'll see them. We're going to look at this in cross section as if I'm looking at the Earth sideways with the lithosphere and the asthenosphere down here. In other words, the crust is the top of the lithosphere, and we would be living as tiny little organisms on the top of that. All right? So, step one is kind of like what's happening in East Africa right now. Here's Africa. East Africa, if you follow that yellow line, along the yellow line, and there's some red transform faults that connect them, but along that yellow line, there's rifting going on. This part of Africa is headed that way, eastward. So the country's literally splitting open, and if you can search videos, and there's farmers that have fields that all of a sudden there'll be a big seam ripped open in it because of the divergence of the continental crust that's underneath this, right? So we're talking to continents, and you can even see right down in here there's water that fills in at the really low spots. Those lakes follow that Rift Valley pretty tight. So if you can play this forward in your head, what's going to happen eventually as this thing continues to rip open and rip open and rip open. So that's really our step one, is let's just say here's East Africa, but there's tension, which means pulling on the crust. It's being split open, so it's going to start to rift here. So phase two, I should have like dotted lines here to separate them. Phase two, same setup. What's going to happen is, this drawing is technically correct if you ever do real geology classes and you have to study what kinds of faults these are. This diagram isn't too shabby, even for me. Alright, so this is kind of like maybe present day East Africa. We still have the tension on the crust. It's being ripped open. You get these types of faults where these blocks drop down, and you get a valley. It's closer to the asthenosphere down here. There's going to be volcanic activity, hydrothermal activity, and of course water, since water flows downhill, is going to want to go down to the bottom of these rift valleys. Alright, so again, going over to East Africa, that's what we're talking about right there. Now if we play that forward even more, we'll go to step three. What's eventually going to happen is you got this over on one side. Sorry, doing this with one hand hampers my already poor drawing skills. We'll still do the bottom down here. Probably should have done that one further away, but what happens is that this gets really thin and might even fill in with water. I'll come up the other side. This side's going to be too steep to be realistic, but it happens. Alright, still rifting. Only eventually you develop a shallow sea. So where's that happening in real life? Well, that's going to be the future of what goes on here as East Africa continues to migrate that way. And we're talking a couple centimeters a year. This thing's not flying. But what eventually happens is like what's going on right here. These were together. This Red Sea is spreading open a little bit, a couple centimeters a year, getting bigger and bigger and bigger and bigger. So this is like our phase 3 diagram down there that fills in. Now if we can play this way forward, what I'll do is this. Now, a lot of you guys, as I asked earlier in the year, had heard this idea of Pangea, that the continents were all together at one point. In fact, it's happened multiple times. These things are always floating around and banging into each other. But if you can play that Red Sea thing forward for 200 million years, this thing's been doing this for 200 million years, but opening and opening and opening and opening. So if we were around 200 million years ago, standing on that rock, that in Africa was connected to that in South America. It rifted into a narrow sea, and then opened and opened and opened and opened, and is still opening. I mean, if you fly from the States over to Europe or Africa, I flew to Ireland when I was in high school. That flight would now be a little bit longer because we're going away from Ireland bit by bit by bit, right? A couple centimeters a year. So playing that forward 200 million years, now what we have is, I'm going to stop to draw those fault blocks because they kind of get as the continents get that old, they tend to be less important. So what we've got is this is a bummer with one hand. All right, oceanic crust. It starts to build brand new oceanic crust at the bottom of this. Eventually, there's not enough continent. Like if you stretch your pizza dough too thin, there's a hole in it, right? Well, you can't just have a hole into magma. What's going to happen is that new magma is going to come squirt, and it's going to hit what is now the bottom of the whole of the Atlantic Ocean, cold water way down there, and form brand new rock. It's mafic, extrusive. I won't make you go back and look. I would if we were in class, but that would be basalt. So this is forming brand new ocean crusts as it spreads bit by bit. This like cracks open and shoves these two continents apart. This could be Africa. This could be the Americas. And now again, it's still happening along this thing, which we call a mid-ocean ridge. I'm going to write that when I stop the camera so that it's neat. It's still happening along this mid-ocean ridge. They're still spreading. And in fact, this is really what drives plate tectonics, is the weight of that pushing down. This is like a mountain range in the bottom of the ocean that's a couple kilometers tall. It's big. And so the weight of that shoving down continues this spread of those two. On this, you can see it like that. If I turn off, you can see it. If you've seen maps that look like this, that's what that big white line is that mid-ocean ridge. All along that, spreading, pushing those continents further apart, creating brand new ocean crust. If you look at the ages of ocean crust, let me turn the boundaries back on. If you look at the ages of ocean crust, there's some forming today, somewhere along that line. And then as you go out, 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 it's older and older, older. Same thing over here. Out, 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 older, older, older. From 0 out to about 200 million years towards the edges. And it's symmetrical. And I'm skipping this thing this year. There's a whole lot that we did. You guys had to do a whole lab on like identifying these magnetic anomalies within this and blah, 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 blah. Congrats. With all the mayhem going on, you get to skip that. But at the end of the day, the point of that lab is that there's a symmetry. This side, if you watch my two fingers, this side flips. This side, they're symmetrical. They're symmetrical, like intricacies within the rock that match all the way out. So it's really strong evidence that these continents were together and they spread and they spread and they spread and they spread and they spread. All right. That's a lot. That's Divergent Boundaries. Watch it a couple times. Again, I'll try to make the quiz easy, but and then just check your reference table again. Tectonic plates, divergent boundaries. That's all mid-ocean ridge system going all the way around. And then really the strongest place where it's on land right now is through that East African Rift Valley. I really dislike that your reference table labels that as complex or uncertain. Yeah, it's like in a couple of weird spots, but it's absolutely a divergent boundary. And it's pretty well delineated. I don't know why they call it uncertain. Oh, New York. All right, that'll do it for Divergent. We'll see you in a few minutes with Convergent.